Hi, I'm Jim Frankenfield. Another video here for my academic website project, jamesfrankenfield.com, and the YouTube channel that goes with that. I haven't made one in a while. I've had a lot of other things going on, and I'm hoping to get back to making videos sometime in the coming months. I came up with a reason to make this one, and this one is going to be on kinematics problems in physics and how to solve general kinematics problems. It really addresses the transition from your first physics course, which is often formulas. You got to find the right number that goes with the right letter and then get out the calculator. Now we have to look at things in a more general sense, and we have to look at equations differently. And what I first wanted to do in this video that I'll get to shortly is the importance of a diagram showing your coordinates. You need to know where your origin is and what axes are, where your x and y axis are, and then you can work from that. So this is how to solve some problems in general, and I will then solve three problems. I was originally not going to solve any problems, just talk about how to organize and set them up, but we will look at three problems. So let's start with the equations that we have and how we interpret them and what they mean. Our basic kinematics equations, and you can solve all kinematics problems basically with these. Acceleration is going to be constant. Okay, we're only going to deal with constant acceleration right now. You can deal with non-constant acceleration. You usually don't do that until much later. If the acceleration is constant, our velocity at any given time is the initial velocity you start out with, plus the amount of acceleration times time. That's this velocity that increases, that you gain from accelerating. And our position, which I'll call R, because it could be X or it could be Y. Some people use R and some use S. I start at some initial position, and I have a velocity times time. So the faster I go, the more distance I gain. And if I'm accelerating, I have to add another term, 1/2 AT squared. So these are the three equations. There's a couple other common ones in one dimension. We often use this is scrap paper here because this is an aside, but we also use velocity final squared is velocity initial squared plus 2a times the distance. There's also an equation I don't remember that gives you the range of a projectile. And you really don't want to go off memorizing a bunch of those things, although they can be useful for certain kinds of problems. But all of those equations are derived originally from these three. So it's certainly easier in certain problems to use this derived equation and use it enough to remember it, but you don't need it. You can always go back to these equations. So we're not going to look at these equations as formulas anymore. We're going to look at them as statements. Okay, these are statements that describe motion in general, and we're going to reduce them to a set of more specific equations for each problem. So each problem is going to have a different, each physics problem is going to turn into a different math problem. So the other thing I want to mention, you're going to need to know a couple things here. I'm assuming a couple of very basic level knowledge of vectors. So these are vector quantities. You have an acceleration in the x direction, the y direction, and potentially a z direction. Your position R consists of x, y, and z coordinates. So all of these are vector quantities except for time. And I'm going to put a bar over top of them to note that. So the bar over top means it has components, x, y, and z components. What this is really saying is a rate of change. Okay, so the velocity is the rate of change of your position. The faster you change your position, the more your velocity is, right? And the faster you're changing velocity means that you have more acceleration. So these are related as rate of change, and when it's not constant, that can be done with calculus. So just as an example, and I'm not going to go off into calculus beyond this, but if this were r0 plus v0t plus t cubed over 6, I would have a different velocity equation. I would have, and this is the derivative of this. The r0 goes away. You get initial velocity. The derivative of t to the 3 is 3t to the 2 over 6. So you get v0 times t squared over 2. And then acceleration would just be t. So the acceleration is increasing with time. And we deal with the rate of change using derivatives in general. Okay, so in the future, if you want to deal with non-constant acceleration, that's how you're going to do it. And it's still a statement about rate of change. Okay, and going the other way is integration. So when you get to the point where you're using calculus, that's more general statement of motion. So that's the equation and the way to think about them. Okay, don't just start looking for things to plug in here. Let's apply these to each situation. Okay, so the first step in any problem solving for these, and actually you have different types of diagrams for different types of problems. In general, in physics, the first thing you want to do is draw a diagram. So let's look at a simple projectile problem first. I fire something at some angle theta with some velocity at that angle, v initial. So here's my diagram of what's happening. What I want to include on my diagram is an origin. So I want to show where is my 0, 0 point. And that's arbitrary. I can put that anywhere. We'll see that in a minute. I could call the ending point 0. I could call 0 100 meters to the left. It won't affect your solution, okay? And in some problems, there's different, maybe a couple different logical choices for this origin. If I'm grading work, I want to know where you put your origin. That helps me see what you're doing, and it helps me match your equations to what you're looking at here. The other thing in general to do in projectile problems, it's usually standard direction. This is my x direction, and this is my y direction. And we can denote those with unit vectors. So I is a vector quantity which points in the x direction and has a length of 1. So that's basically just telling me that's my x direction and that's my y direction. We will do one problem in a moment where I put the x direction the other way to the left because that's the way the motion is. You don't have to do that. You could introduce a minus sign. So there are different ways you could do that. And start out by showing what your coordinates are and where your origin is and what the motion looks like. This is a simple projectile here. We're going, I guess now also introduce at the beginning, we have some velocity v0. We're firing this at an angle theta I initial. So we need to find, because these are vector components, we need to find the initial x velocity. And the initial x velocity is using trigonometry. This is as much trig as you need to know. Right angle trigonometry. Cosine of theta is the adjacent side over the hypotenuse. So this will be cosine theta I times v0. So it's this side times cosine theta. And the y component will be the hypotenuse times sine theta. And sometimes we need the tangent. So the tangent of theta would be the y velocity over the x velocity, opposite over adjacent. Okay, so you need to know a little bit of right triangle trigonometry, but that's about it. And also you should know the Pythagorean theorem by now. A squared plus b squared equals c squared. So if I know the two right angle sides, I can calculate the other side. We're going to be using that a couple times. And that's pretty fundamental to doing any kind of kinematics projectile type problem. So, okay, that was my denoted part 2. Let's go on to a problem here. Okay, so part 3 of the video, let's look at a problem. This is, I don't remember which edition this is. It's from Holiday and Resnick, which is a classic textbook. Let's read the problem. Okay, a small ball rolls horizontally off the edge of a table. We know the height of the table. We know how far the ball goes. We want to find out how long it's in the air and how fast it was leaving the table. So we need to draw a diagram for this. This is a very classic introductory problem that was chapter 4, number 22 in whatever edition this is. So here's my table. There's a drop to the floor, and this floor is over here. And I have a ball, and it follows a trajectory like this. It hits the floor over here. And this is a distance of 1.52 meters, and this height of the table is 1.2 meters. So there's my diagram. Let's look at two different origins. First, let's use this as our origin. So this is 0, 0. And I'm going to use the standard coordinates. There's no reason to do anything different. So x is to the right and y is up, plus x is right and plus y is up. And let's write down over here what we want to find. We want to find t, and I want to find v0 in the x direction. There is no initial y velocity up and down. So let's write down our equations for the x and the y. We have ax, we have vx, and we have the distance x. And there's no acceleration, and this is true in most projectile problems. There may be some exceptions. They would probably be harder problems. There's nothing accelerating this left and right, so that's 0. Velocity is the initial velocity plus acceleration times time. Acceleration x times time, and the x is my initial x position plus initial x velocity time plus 1/2 axt squared. So these are my general equations, but in this particular case, I'm going to come up with a set of specific equations, and I'm going to do that by crossing that out. There's no ax term, which means that is also gone. And x0 in this case is at 0. I'm starting at x equals 0, so that goes away. So my x equations I can use are vx equals v0x. So the x velocity is constant. And my distance x is equal to that initial velocity times the time it's in the air. Now I'm going to do the same thing in the y direction. So most of our problems that are projectiles and subject to gravity is 9.8, and it's downward. So note that my positive direction is upward. This is downward, so it's minus 9.8. I'm going to use minus 10 just to keep things simple. In a class, some professors and teachers let you use 10 or encourage it. Some will insist on 9.8. Obviously, for real world work, you would use an accurate value. So we have velocity in the y direction. We have our initial y velocity plus a y t, and y is equal to y0 plus v0y t plus 1/2 AYT squared. So we can reduce these. We're starting, let's see, V0y. Is there any y initial velocity? No, we don't have that. We're starting at y equals h. This was 0. So these equations are, and I'm going to leave out the a because that's constant. We have a velocity y at any time is equal to minus 10t, right? And we have the distance y at any certain time is the initial y minus 1/2 ay, that's 5t squared. So I've taken my equations of motion that describe motion in general, and now I have a specific set of equations for this problem. And for a different problem, they'll be different. So what I've done at this point is I've taken my physics problem and I've reduced it to a math problem. And a lot of times the difficulty of a physics problem may come down to how difficult the math is. Some problems are easy to solve, and some problems can be present a more challenging mathematical problem. So let's see, we know y at the ending point, which is 0. So let's use that. 0, y0 was 1.2, which was h, right? Let's just call it h, minus 5t squared. So 5t squared has to equal h, which is 1.2. And we can find t from that. T is equal to 0.49 seconds. So I'm going to double underline that. That's one of my solutions. And I found one of the things I needed. Now I can come over here and look at the end point, and I have the distances when x is equal to d. I have v0x times t. I can find the initial x velocity is the distance over time, which is the distance it reached is 1.52 over the time, which is 0.49. And I get 3.10. So I found the two things. This one was a fairly easy problem. The main point is to start out with a diagram showing your origin, showing your coordinate system, and then take your full set of motion equations and reduce them to a math statement for this particular problem. Let's look at one other possibility here. There's another place that is pretty logical to call my origin. This could be 0, 0 up here at the top, right? So now the edge of the table is 0, 0. Let's look at this equation and rewrite it as x minus x0. So I'm moving this x0 over to the left, and that's going to equal v0xt, right? And what's x minus x0? This minus this, 1.52 minus 0 equals 1.52. So that's what I had before. Once I find t, I can find that. Let's do that over here. Y minus y0 is equal to 1/2 ay, that's minus 5t squared. Well, what's y at the end? Now y is equal to minus h, right? So y0 now is 0. And y final over here is minus 1.2. So I get the same solution that I had up here. If I did this one up here the same way, I would have y minus y0 equals minus 5t squared. Well, now y at the end is 0, and the initial y with the black ink in the original version was 1.2. So I end up with the same thing either way. When you rewrite it this way, y minus y0 and x minus x0, you can see that it's this difference that's important. This is the distance it traveled. It doesn't matter what you call 0. I could put 0 2 miles to the left and the difference would still be 1.52. So your origin is something you can choose, and sometimes that makes a problem easier or more difficult to solve. Okay, onward to another one. Now this one's a little bit harder. Let me pull this down here. Okay, so this is another one from the same textbook, same chapter, chapter 4, Holiday and Resnick, number 39. It's got 2 dots, meaning it's a bit harder. So we're throwing a ball leftward from the left edge of this roof. And we know how long it's in the air. We know how high the building is. I think, now we have to find that. So that's h. And we know how far from the building it lands. And we know the landing angle, which is a bit unusual. So that makes this problem a bit unusual. They're giving you a hint to reverse the motion. So they're saying that that you could solve it as if you launched the ball from the landing point over here and it landed on the roof, and then you could translate that back to the original problem. I'm not going to do it that way. I'm going to set up a diagram. One thing about the Holiday and Resnick in this edition anyway, I like the older editions, but the oldest one that I learned from, it's 3 volumes in green, doesn't seem to be online in PDF at all. And some of the solutions in the solutions manuals for these other editions take shortcuts, or they do go back to a formula they derived somewhere in the text and put numbers in the formula. And that kind of defeats the purpose of what I'm trying to do here, which is to teach you not to do that, to start from fundamental principles and fundamental set of equations and work from there. So I'm not going to use that hint. Let's make our diagram again here. So, and then let's write our equations. And solving them will be a little bit more difficult this time. So I have the ground over here, and up here is the building. And let's see, I'm going to land over here. Oh, it's not going that way. It's going this way. So this is 60 degrees because this is 60 degrees. And it launches at some initial angle that's not given. I don't know what the angle it was thrown at was. I know that the time is equal to 1.5 seconds. I know this is 60 degrees. And I know that this distance to the landing point is equal to 25 meters. Let's just double check that. Yeah, 25 meters. So we're moving to the left, so I'm going to use a coordinate system with my positive I direction to the left, which is not our standard common one, but there's nothing wrong with doing that. Let's see, and I know that my initial x velocity is going to be my initial velocity times cosine, and this is what I was mentioning earlier, a little bit of trig that you do need. So this initial velocity, which is a vector going that way, it has an x part and a y part. The y part could be up or down, and we'll see that in a moment. So let's write our equations. Ax is equal to 0. There's no x acceleration. We generally ignore winds and wind resistance, air resistance. Velocity in the x direction, therefore, is my initial velocity plus at. I'm going to cross that out. My x distance is x0, which is what? I didn't put my 0 on there, did I? I didn't go back to do that, which is one of the things I'm trying to emphasize. Okay, I'm going to put my 0, 0 at the corner of the building up here at the top. And there's a little distance because presumably it's not launched from the corner, but we're going to pretend it's launched from the corner of the building. So that's the launch point. Maybe if it's a potato cannon or something like that, you could set it on the corner. If it's a person throwing it, there's going to be some other distance there. So x0 is going to be 0, and I have v0xt plus 1/2 axt squared. I'm going to write this out each time. Sometimes after a while we don't do that, but you can include and address any kind of problem if you include all these terms. We could have an x acceleration, and we just wouldn't cross that out, that's all. And the math would be harder. In this case, we're going to cross that out, and we're going to set this 0 because of my coordinate selection. If I put the origin somewhere else, that might not be 0. So again, I have Vx is equal to V0x, and that's constant, but I don't know what it is. And x is going to equal whatever that is times the time. Let's go over here. Ay is going to equal minus 10 again. I'm going to use 10. And I'm being sloppy, as we often are, with units. That's meters per second squared. Sometimes if you get confused, the units can help you sort things out. There shouldn't be any unit issues in this case. Vy equals V0y, which I don't know, plus ayt, and y is equal to y0 plus v0yt plus 1/2 ayt squared. So there's my full set of equations. I can't cross this out, and I can't cross this out. I am starting at a y equals 0, so I can get rid of that. There is a y velocity at the beginning, so I can't get rid of that or that. So these equations, now I have Vy at any time t is the initial y minus 10t. And my y position at any time t is the initial velocity times t minus 5t squared. So these are the equations that I'm going to work with, and I'm tempted just to leave it to you to solve them, but it is a little bit tricky. So let's take a quick look at that. Let's see, what do we know here? Well, let's start with this one. So when it lands, what's y? Y at that point is minus h. We don't know h. That's one of the things we need to find. And that's equal to v0y times t, which we do know is 1.5 minus 5t squared. But I don't know this, and I don't know this, so I can't solve this yet. Let's just label it A for later. If I can find the initial y velocity, then I can find h. So how are we going to do that? Let's see, we know, well, let's come back over here and find our initial x velocity. So what's x when it lands? That's 25. That's equal to the initial Vx, which I don't know and I want, times 1.5. This allows us to find the initial x velocity. And that turns out to be 16.67 meters per second. Okay, now I've got the initial x velocity. Let's see what we get. And we know, well, this is also equal to the v final x, because I know the angle over here. I don't know this angle, so I need to work with this point. So what I have over here, let's draw our triangle. Here's v. I'm just going to use some scrap paper here for this one, for side work. This is my v final, this is my v final y, and this is my v final x, which I just found to be 16.67. And this is 60 degrees. So the tangent is opposite over adjacent. Tangent of 60 is equal to v final y over 16.67. So that gives me that my final y velocity is, let's see, minus 28.87. And that's minus because this final velocity, it's hitting the ground, so it's hitting the ground this way, which means the x is to the left, which is positive, and the vy is downward, which is negative. So that gives me my final velocity here. Now let's go back to, we still can't use this equation because I need my initial y velocity, but now I know the final y velocity, and I can find the initial one from this equation. So I got minus 28.87 is equal to v0y minus 10 times 1.5, and this lets me find my initial y velocity. Initial y velocity then is minus 13.87. Gotta move this down a bit. Okay, so now that I know that, I can come back to equation A. As I know this value and I can find h, I'll let you do that. H turns out to be 32.05 meters. So we found h. And that's a little bit tricky to figure out what to do. And aside from these equations of describing the motion, we had to use our trigonometry here at the final point, and then go back to the initial point. So figuring out how to solve the math in this case is a little tricky. Maybe it may deserve 3 dots the way I did it. They give it 2 dots, but they're telling you to do it backwards and treat it as moving from the ground to the roof. Perhaps that's easier, I don't know. But the point here is you can do this using your fundamental equations, selecting an origin, and using its appropriate coordinate system. There were a couple other points on here. Let's see, we need to find the magnitude, and we need to find the initial angle and velocity, which I think we've already done basically. So we now know that the initial y velocity is, we found that, minus, well, let's see, is minus, so downward, 13.87. And the initial x velocity is 16.67. So to find this, the magnitude of v0 squared is equal to 16.67 squared plus 13.87 squared. You'll get the magnitude of the velocity is equal to 21.7 meters per second. And you can find this angle, tangent of the theta initial is equal to the y, which is 13.87 over 16.67. That's for this angle. Okay, that's opposite over adjacent. And you'll get an initial angle of 39.8 degrees. But we have to pay attention here, and sometimes with using trigs and angles, sometimes you have to look at your diagram. This is actually in relation to the horizontal. So this is below horizontal. So this actually was not fired upward. It was actually fired or thrown at a downward angle like this. It's still going to be a parabolic path, but it's starting out at a downward angle, which may not be what you expected. You kind of assume when you read the problem that it was thrown upward. So that's another one. Again, going back to what we want to focus on here, we started with our full equations of motion. Always start with those. We started with a good diagram we can work from, and we also had a scrap paper for dealing with triangles and other things as kind of an aside. If you can't do that in your head, it's probably better to do it on paper. We selected our origin and we selected our coordinates, and I selected positive to the left. If you made positive to the right, you'd have some different signs in here. Okay, so the last one is actually a fun one. This is another very classic problem. It's actually from chapter 2 in the book because it's one-dimensional problem. Let's see, let's look at that. So, yeah, this is kind of a famous problem. We can zoom in a little more here. The drowsy cat and the flower pot. So the cat's looking out the window. He sees a flower pot someone threw out the window, I guess, and it goes up and then it comes back down. And it's in view a total of 0.5 seconds. Okay, so you got to be careful with that. That means it's 0.25 seconds going up and 0.25 seconds coming down. And we know how high the window is, and we want to know how high above the top of the window the flower pot goes. So let's draw a diagram here. And I start out somewhere, the ground or some window down below. That's where it started. I'm going to call x0 the bottom of the window. x1 is equal to 2 meters. That's the top of the window. And x3 is going to be the height, or x2. That'll be the height that we want. I don't really care about this part. You could probably go back later and figure that out. I'm going to call this, and this is one dimension, so I can use x. Y might be better because it's vertical, but I started with x, so we'll use x. X equals 0. Well, how high is the window? This is 2 meters, and this is h meters. And I only have one direction. I'm going to call up positive. Sometimes with something like a dropped object, you may want to call positive downward. Then your acceleration would be plus 10. So I have my diagram. I have my coordinate. I'll put I on here, but it's irrelevant. I can put I anywhere, any direction I want here. And 0, 0 is wherever the bottom of the window is and goes by. But the horizontal coordinate doesn't matter. So let's write our equations. And this time I only have a y equation. Acceleration in the y direction is minus 10. Vy is equal to v0y, which I don't know. That's the velocity as it goes. I'm going to look at motion up. Okay, I'm going to look at one direction. So it goes, you can think of it as starting here with some initial velocity. Think of it as being thrown from the bottom of the window. It actually came from below, but we can think of it as starting here. Minus at, so that's minus 10t. And then I have the y distance is equal to y0. plus v0y, which I don't know, times time, which I actually do know, minus 1/2 at squared. And I'm going to call this 0. So let's look at the first coordinate at x1. What is the height? What's y at x equals 1? Y is equal to 2. I'm kind of interchanging x and y here now. Sorry about that. But y is distance is 2. And that's equal to the initial y, the velocity at the bottom of the window, times the time to get to the first top of the window, which is 0.25, minus 5 times 0.25 squared. So this very immediately gives us the initial y velocity. So we know we know its initial velocity as it comes up past the bottom of the window now. And we can use that to look at what happens at x2. Now at x2, we have to use what's going to happen at x2 to the velocity. It's coming up and it's turning direction. So for a moment at that height, Vy is equal to 0. Let's call that V2y at 0.2. So at instantaneously at the top, it's not moving. It's going to slow down, hit a 0 velocity, and then speed up coming back down. So that's going to allow me to use this equation here. Vy, so Vy is equal to 0, and that's equal to the initial velocity, which is 9.25 minus 10t. I'm going to call this t prime. This is not the 0.25 to go past the window now. This is the time to go from here to here. And I can find t prime that way. So t prime turns out to be 0.925 seconds. That's how long it takes to get to the top. So how high is the top? Well, now we use this equation. Y3 or x3, whichever you want to use, x or y, that's equal to V0y, which is 9.25, times t prime, which is 0.925, minus 5t squared, minus 5 times 0.925 squared, and this gives you 4.28. But that's not what they asked for, and this is something to be careful. So the first thing to note is that at the top of a trajectory, and this is true for any kind of projectile problem. Let me use my scrap paper here again. Okay, when I have a projectile, at the highest point, it has a constant x velocity everywhere because there was no acceleration. But Vy at the high point is 0. That's a fact that's often useful. The second thing to remember here is that when you're done, make sure you're answering what they asked for. There are a lot of questions where it's very easy to just throw out an answer you found, which isn't what they wanted. They want to know how high above the window top does it go. Okay. Whoop. And the distance to the top, what I found was h from the bottom of the window. That's 4.25. So I have to take the 4.28 rather, and I have to subtract 2 meters for the window, and I get 2.28 above the top of the window. So in terms of our diagram, this is what I want is y2 minus y1 from the top of the window to the high point. So that's equal to y2 minus y0. That's the whole height minus y1 minus y0, which is the window height. And this was 2 and this was 4.28. So if you just solve the problem and feel like you're done and quickly write down 4.28, you won't actually be answering the question that was asked. So that's how to solve several of these problems that are tricky. And solving the math and figuring out how to work with the math problem you end up with takes some practice and time, and that's where experience comes in. The first part of all of these problems started out the same way. We drew a diagram. We used the same set of fundamental equations for every one of those problems. We identified our origin. We said which way was plus x and which way was plus y. And then we reduced those general equations to a set of equations for our problem. We reduced it to a math problem. And that part you should probably be able to do for almost any problem. How to solve those is a little bit more difficult, especially in that second one. That was not obvious how to go about solving that. But we came up with the, let's see, I think this was the page. We came up with the equations we needed. At that part, you should be able to do. If you haven't done enough of these yet, solving it from there may be a little bit harder. The Flowerpot problem looks easy this way, and if you look at other solutions, you'll see other methods. You can end up using this equation, this derived equation in one dimension. I didn't want to do that. I wanted to do it like everything else from the fundamental descriptive equations. It is a little bit tricky there in that Flowerpot wanted to know how to set it up, where to put your origin, how to come up with the equations. And it looks simple once you figure that out, but figuring out where to put the origin and how to apply the equations is a little tricky in that one. Anyway, I hope that helps you see how to solve kinematics problems. There are all kinds of variations of projectiles. There are, motorcycles jumping TV towers and things like that. And there are all kinds of, sometimes you have to find the angle that you launched at, which we did in the second one. Certain combinations of things you don't know can turn out to be even difficult to solve and requiring something like Newton's method from calculus. That's very rare. Most of the time you can solve the equations using general algebra. So take that approach and you'll be able to solve anything as long as you figure out how to adjust the math. Okay, so that's it. That's much longer than I thought, but that's because the three problems take a lot of time, and I did go through how to solve them, even though the emphasis is really on how to set them up. So that's it. I don't know when my next video will be. I hope it'll be not too long, but I still have a lot of other things to do this year. So till then, bye.